A guest taps a self-order kiosk to add an item. Nothing happens. Assuming they missed, they quickly hit the screen again. That second tap pushes a duplicate order into the system. The guest now has 2 identical entrees in their digital cart when they only wanted 1. The transaction immediately halts. The guest has to flag down an employee, forcing that staff member to abandon the prep line, walk over to the kiosk, and manually input a manager code to void the extra ticket. These frequent touch errors represent a direct and measurable leak in unit margin. A self-service kiosk exists to increase ticket volume and reduce labor overhead. The moment an employee intervenes to fix an interface error, that baseline mathematical advantage disappears. As the hardware stutters and guest frustration builds, the perceived efficiency of the machine drops. Customers notice the frustrating delays and organically shift their volume back over to the traditional human cashier line. Excessive latency cannibalizes the location's average order value by driving users away from your primary digital upsell engine. To understand why a minor delay causes such a severe reaction, you have to look at the physiological baseline guests bring into your restaurant. They are neurologically conditioned by the devices in their pockets. Modern consumer smartphones process and respond to physical touch events in under 50 milliseconds. This diagram shows 2 response timelines. The top track represents the smartphone standard, 50 milliseconds from contact to visual acknowledgement. The bottom track shows a lagging kiosk taking hundreds of milliseconds. The strict physiological limit to human patience sits at exactly 100 milliseconds. If the time between a physical tap and a visual response crosses that 100 millisecond threshold, the brain instinctively categorizes the hardware as broken. A user will evaluate the complete technological viability of your ordering system within the span of their first 2 physical taps. Consistently exceeding the 100 millisecond threshold forces guests to reevaluate the kiosk's utility, frequently leading them to abandon the transaction before completion. To fix latency, we have to look past the external casing and deconstruct the physical architecture of a commercial kiosk to find the bottlenecks. The first critical point of failure sits right at the surface, the touch panel layer itself. When purchasing fleets, budget-conscious procurement teams frequently default to ordering resistive touchscreens because they are cheap and industrially durable. Resistive screens rely on an outdated mechanical mechanism. They require the user to apply deliberate physical pressure to push 2 interior layers together to register a signal. That mechanical requirement inherently introduces a delay. The modern non-negotiable standard is PCAP, or projective capacitive technology. PCAP registers the electrical conductivity of human skin upon contact, eliminating the need for physical pressure and capturing the signal instantly. But capturing the signal is only half the process. Translating that physical touch into a digital action requires the internal compute module. Entry-level industrial PCs equipped with basic processors simply lack the computational horsepower to render complex, modern visual interfaces without stuttering. When you pair a weak processor with limited RAM and sluggish, spinning hard disk drives, the internal data transfer is severely throttled. Compromising on baseline compute power permanently caps the maximum responsiveness of the machine. The fastest software in the world cannot overcome physical hardware bottlenecks. However, premium hardware guarantees nothing if it is running unoptimized code. The primary offender at the software layer is raw content bloat, which forces processors to work harder than necessary. A common operational mistake is loading massive, uncompressed 4K resolution hero images into a kiosk application that is running on a standard 1080p display. Because the display cannot handle the native resolution, the processor is forced to mathematically downscale those massive graphics in real time for every single frame. This background resource drain eats up critical CPU cycles, directly causing the interface to stutter and introducing heavy input lag. That specific software lag is the direct mechanical cause of the double tap error. The user taps the screen. The bloated software is too busy resizing images to process the input immediately. The user assumes the machine failed to register the touch, and they strike the button a second time. Look at this line graph mapping touch inputs. We have 2 sharp physical interactions, T1 and T2, occurring just 200 milliseconds apart. To stop the double order, the software requires a protective mechanism known as debouncing.
Debouncing is a specific configuration in the code that instructs the system to automatically ignore any rapid, repeat physical taps that occur within a set time window, usually around 300 milliseconds. Without that strict 300 millisecond logic block in place, the system blindly accepts both rapid inputs, instantly generating a duplicated ticket in the kitchen. A missing debounce configuration is purely a software oversight. It is a few lines of code that any competent vendor can implement. But code logic alone doesn't solve the user's impatience. You still have to account for the psychology of visual feedback. Even if the Kiosk application legitimately needs 200 milliseconds to process a complex card addition in the background, the user interface must acknowledge the physical touch instantly. Programming a button to change color on contact or triggering a rapid touch ripple animation provides the immediate visual confirmation the human brain requires. Debouncing logic and instant visual feedback function as critical software failsafes, protecting restaurant margins by neutralizing the impact of human impatience. Preventing margin leaks starts before the hardware ever reaches the restaurateur. It happens during procurement. Operators must stop accepting vague, unquantified assurances from sales reps claiming their kiosks are fast and responsive. You must mandate strict, highly documented hardware minimums into all future requests for proposals. Your procurement hit list should dictate exactly what you see here: PCAP capacitive touch panels, an Intel Core i5 processor equivalent or higher, a minimum of 8 GB of RAM, and fast NVMe solid-state storage. Above all, you must contractually mandate a sub-100 millisecond touch-to-feedback latency standard before signing off on a fleet rollout. Simultaneously, force your software vendors to explicitly prove that debouncing configurations are active and properly tuned in their application builds. Enforcing precise technical specifications at the RFP stage is the only reliable method to prevent the hardware from compromising your operational throughput later. For the kiosks already deployed in your restaurants, performance management requires active testing. Kiosk compute power is not static. Physical components degrade, and software applications accumulate data junk over months of continuous operation. Thermal throttling from trapped heat, alongside invisible software memory leaks, drive a gradual, creeping slowdown across the machine. Store managers need to institute a mandatory friction test during their regular weekly floor walks. The process is simple. Intentionally strike the screen buttons as rapidly as possible. This stress tests the system to verify that the debouncing threshold is still active and successfully blocking duplicate inputs. If a kiosk registers a double order during this friction test, managers must demand immediate software patches or remote memory wipes from their IT vendors. You have to actively hunt for latency in your fleet. If you wait for guests to complain about slow screens, the financial damage has already occurred. A highly responsive, sub-100 millisecond kiosk earns the customer's trust and protects your unit economics. A lagging system frustrates the user, hands that revenue straight back to a slower counterline, and defeats the entire purpose of the technology.